I want to start by welcoming you and thanking you for joining us to today's event. My name is Miguel Garcia Garibay. I'm the Dean of the Division of Physical Sciences. Currently, I also serve as the Senior Dean of the College of Arts, Letters, and Sciences. So perhaps some of you saw the news maybe 3-4 days ago. So of course, based on those news, I have to brag about it. You probably saw that U.S. News & World Report again ranked UCLA the #1 public university 8 years in a row. I mean, you might think that it has to do with the food at the dorms or something like that. But no, really, it is the quality of our faculty, the amazing student body that we recruit, some of the most diverse and talented students really in the country and across the world choose UCLA. You probably also know that we are the most applied to university. This year, we broke the 170,000 application barrier, precisely, right? So that means that we have an opportunity to select the best of the best by looking at many, many variables. It's a multi-variable, approach to admissions. And every student you see walking out there in our campus is brilliant in her or his own way. But one thing that most of them have in their DNA is leadership. They're all fantastic in terms of GPAs and every other metric. But one of the things that our students do have is leadership. And many of them are first in the family to go to college, about a third of them, in fact. So we are also ranked very highly as one of the universities that are considered an engine of social upward mobility. And all of that in the context of really amazing science and technology that goes on. So as Dean of Physical Sciences, I interact most with the departments in the division. And those are the departments of Atmospheric and Oceanic Sciences, the Department of Chemistry and Biochemistry, Earth, Planetary, and Space Sciences, the Department of Mathematics, the Department of Physics and Astronomy, and the Department of Statistics and Data Science. We also host some of the most interesting interdisciplinary institutes and centers in the university. Among them, the Institute of the Environment and Sustainability, that brings together scholars from really all disciplines to tackle some of the most interesting challenges in the environment. So UCLA's, the research at the UCLA Division of Physical Sciences, it really is a catalyst for discovery and innovation, helping drive many of the technology sectors that are developed in our state. The division has some of the most entrepreneurial faculty with record number of patent applications, patents granted, patents licensed, and even startup companies. So the extent of innovation that goes on here is truly, truly remarkable. I was in previous conversations saying that it's come to the point that division like ours, Physical Sciences, really relies on intellectual property income, not quite as much, but getting close to as much as we rely on philanthropic contributions, both from foundations, companies, and individuals. As you know, higher education research is going to a transformation where the state is kind of the funding, but fortunately, individuals and corporations and foundations are coming to the rescue, making universities healthy so they can continue developing some of the best science and technology. We really contribute to the economy, both in terms of inventions and discovery, but also let's not forget that we are also preparing one of the most diverse and talented workforces in areas of emerging areas of science and technology. So today's event, Quantum Sensing for Humanity, brings together designers, builders, and users of quantum sensors for discussions on the utility of these revolutionary concepts and devices. Sensors in general consist of devices and systems that interact with the environment and provide a measurable response. Introducing quantum mechanical phenomena to sensor technology will affect our decision-making on everything that we interact with from the water we drink, the air we breathe, and medical treatments that will make personalized medicine a reality, all based on the best possible data measured by quantum sensors operating at the limits of the law of physics. Before I introduce our panelists, or actually I will let them introduce themselves, I would like to invite Jeff Miller, the director of the California NanoSystems Institute, to give us some brief remarks. Please, Jeff.
Well, thanks, Miguel. And it's my pleasure to welcome all of you to the California NanoSystems Institute at UCLA. We were founded through a public-private partnership between the state of California, the University of California, and California Tech industry sponsors. And our mission here is to leverage this public and private investment to catalyze research at interfaces between disciplines, in nanosciences in particular, to translate our discoveries into commercial enterprises, and to educate the next generation of scientists and engineers and entrepreneurs. And to accomplish that, we have this beautiful facility you're in right now, which houses a collection of centers that develop and provide technologies for visualizing and measuring and creating and discovering at the nanoscale. We have a startup incubator right in the middle of this building with some 30 startup companies that are translating discoveries made in UCLA laboratories into commercial enterprises for the benefit of society. And we also have meeting and interaction spaces like you're in right now, and we're very grateful for this. But I think most important, we bring together about 350 different faculty investigators from departments in engineering, physical sciences, life sciences, biomedical sciences, clinical sciences, to solve problems that none of us could solve alone. And it's this dedication and real belief in multidisciplinary team science that keeps this institute going. And I think that's a fitting backdrop for what we'll be talking about today in terms of quantum sensing, where you need these kinds of multidisciplinary teams with deep knowledge and the ability to talk to each other and to share ideas, to develop applications that are, for many of us, beyond imagination almost, and hopefully will help us solve some of the major problems we face. So with that, I'll turn it back to Miguel, and thank you all for coming. We're looking forward to a great program. Thank you.
Thank you very much, Jeff. So next, what I'd like to do is I would like to invite our panelists to introduce themselves and their research. Maybe we'll start with Professor Andrea Bertozzi.
Hi, my name is Andrea Bertozzi. I'm a professor in mathematics at UCLA. I also have a position in the Mechanical and Aerospace Engineering Department, and I'm a member of CNSI. My research is very broad, but for the relevance here, I've been working on problems in data science and remote sensing for about 15 years here at UCLA. And I'm really enjoying this collaboration where I get to bring some ideas that have been fully developed in the remote sensing community into a very, very new space of soon-to-be solved problems. Right? Thank you.
Thank you. Sergio?
Hi, everybody. Welcome. My name is Sergio Carbajo. I'm a professor in engineering and also in physical sciences. And I also have an permanent appointment at SLAC National Laboratory that's in the Bay Area, Department of Energy. We look more into the experimental and measurable aspects of light-matter interactions, anywhere from basic sciences all the way to translational applications. So in the context of this meeting today, I'll be talking more about the actual technology, the chips, the lasers, the detectors, the gadgets, so to speak.
Suzanne.
I am Professor Suzanne Paulson. I am in the Department of Atmospheric and Oceanic Sciences. I also have an appointment in the Institute of Environment and Sustainability. And And I work on, the central thing that I work on is air pollution, but I also work on the interface between air pollution and climate. For example, on cloud water chemistry, clouds are the largest source of uncertainty in climate models. We also work a lot on trying to understand what it is about particles that makes people sick and how particle concentrations and what their chemistry is and how that varies in urban areas in the United States, as well as these days also in parts of Africa. And I would say, you'll hear me say this again, but my field is so hungry for more measurements and more sensors, and as a result, I'm super excited to be working with this group and potentially contribute to coming up with new ways of making measurements that we so desperately need for so many different problems that we have.
In the interest of making sure something works, I'll use the same mic. Thank you all for being here. My name is Prineha Narang. Nobody calls me that. I go by Pri. I'm a quantum scientist and a quantum technologist. I'm one of the sensor designers and builders that Miguel mentioned. And when I got into quantum science, it was not something that would have typically interacted with somebody as awesome as Suzanne. But I'm really excited to tell you about some of the work we're doing in using quantum devices and quantum sensors to impact people's lives.
Wonderful. Thank you, Pri. Thank you, everybody. So to get things going, what I like to do, I like to start with a couple of questions for Pri, and then I will actually ask her to lead the conversation. So Pri, let me start with sort of the basic, right? So why quantum, and what does it do for us in sensing?
Okay, my perfect favorite question, why quantum, all right? So when you think about quantum technologies, and you've maybe been looking at your favorite newspaper recently and seeing that quantum computing is coming, it's here, it was here 5 years ago. I want to remind you that quantum is compute, network, and sense, right? And when we think about quantum sensors, these are devices that interact with the environment. A bad qubit essentially makes an excellent sensor. And the power of quantum mechanics is that we can access sensitivities that we would not be able to with even the best possible classical sensor. Even if every piece of it was operating at its own quantum limit, it would not be as amazing as a quantum sensor. So we're using properties, could be quantum spins, it could be light-matter interactions, so non-classical states of light, and maybe we could get super fancy and also use entanglement to think about how to sense things around us. Quantum sensors in some form have been around for a while. In part, they've been used to measure fundamental constants of nature. We think about how best to do a measurement of gravity, for example. But that's not the only use of these sensors. And what's becoming more and more possible now is that these sensors can be deployed. They can be deployed outside our labs into the environment. They've gotten to a size, form factor that looks about yay large, not yay large or room size, and use them to think about the environment.
Wonderful, thank you. Okay, my second and last question before I give you all that chance to basically have a conversation. So why is UCLA ahead of the curve on quantum sensing?
Okay. So a handful of reasons, and a majority of that is actually seated right here. So this is an area where translating sensors from the lab out into problems that actually have impact requires some thought, right? So as I mentioned, these sensors have been around for a while, but finding the right problem for these sensors, there's many, many different types, whether you're using non-classical states of light, whether you're trying to think about where they're located or how or what you do with the data measured from these sensors, something that Andrea will tell us about. This is the type of science that requires people from many different fields to come together and learn together and figure out what's the problem that we should work on. That's something that UCLA enables us to do. It's something that brought me to UCLA. It's also something that's brought many students who are all here in the audience to work on this topic. This is an area that I'd say has the potential for near-term impact. So unlike areas that promise something that's 10, 15, 30 years out. We need better sensors today. We'll hear about that from Suzanne. And these are sensors that could be ready to be deployed as soon as tomorrow, if we could make it happen.
Okay, I'll let you continue with the discussion.
Thank you. Thank you so much, Miguel. So my first set of questions are for Suzanne. And perhaps you could tell us about the top 3 or maybe 5 things that we want to measure and where these sensors could have this impact that I've been talking about.
Oh my goodness, that is such a hard question for me to answer because my wish list is just endless. I want so many things. I want sensors that are more sensitive, that are cheaper, that can measure things that these days we can probably measure, but maybe it's one lab in the world and it costs $100,000+ a year to run that lab. I want better time resolution, better spatial resolution. I want so many things. But if you want to ask for just 3,
that would be ideal.
okay. Then I'm going to start with bioaerosols. This is something that we have actually gotten a little tiny bit of seed funding for, and we've been thinking about it in a little bit more detail. Bioaerosols include the things I'm sure can all think of: viruses, bacteria, fungal spores, and pollen. They span a really wide size range, so they turn out to be kind of different problems. And they are a small number of the large number of particles that are floating around, but they have disproportionate impacts on infectious disease, on obviously allergies, mold problems. They also have impacts on climate. They're important in how ecosystems function. There are crazy things like there are some bacteria that have designed themselves to make plant leaves freeze, and it turns out they go up into the very upper atmosphere and form ice clouds, and that's super important to understanding our climate. So bioaerosols is an area where we think we can make a lot of progress and have applications right away. Another thing I would pick is a set of chemicals that are really hard to detect in other ways. These are species that are at very low concentrations, but they're at really low concentrations because they're super reactive and they do a lot of really important reactions, or they're really just sticky and kind of semi-volatile and really hard to get into a detector. And with quantum sensing technology, there's potential to really move the needle on some of these measurements, things like hydroxyl radical, ammonia, sesquiterpenes, organic hydroperoxides. And then probably my last one is near and dear to my heart because I think it has so many health impacts, but it's hard to measure, and so we really don't make much progress on it. And it's especially important in the developing world, and that is ultrafine particles. These are particles that are directly emitted from combustion sources, and they can be present at extremely high concentrations, like, for example, in a little sugar cube-sized bit of air. In this room, we probably have about 500, 800 particles in each sugar cube of air. There are roads in the developing world where there can be 10 million of those particles in every sugar cube of air. And we can measure those, but the instruments are way too expensive to have many applications and to be able to understand their spatial heterogeneity and understand the sources, and there's so much potential. I could go on and on and on, but I'll stop there.
Awesome. So it seems like there are a lot of challenges that could be solved, but why quantum? Are there things that quantum sensors could do for these problems in atmospheric science that would be particularly impactful? Is it sensitivity? Is there more than that? And what can we do as sensor builders to measure everything you just talked about?
Sensitivity could be huge for some applications. Definitely size. Sometimes we want to measure the vertical profiles, how it changes as we go up in the atmosphere. We want to put stuff on a balloon. We can't put giant instruments room-size instruments on balloons, so small light sensors would be incredible. Another thing that you wouldn't have necessarily thought would be important, but quantum sensors, I think, uniquely have the ability to measure the surfaces of particles. And it's incredibly difficult to measure the surface of particles. We have lots of measurements of bulk properties of particles, but the surfaces are really important, especially for a lot of climate applications as particles interact with clouds. Also for the potential to do species-specific bioaerosol sensing comes from the ability to potentially look really at the surfaces. And these would be potentially huge tools to advance science and public health and climate.
Thank you. So as we're thinking about some of these sensors, perhaps Sergio, you can tell us how we'll get to everything being on chip and scalably manufactured.
Yeah, let me answer that question in a moment. But I feel like it's incumbent upon me. We keep talking about quantum, right? I want to perhaps provide more specificity to, okay, what do we mean by quantum sensors, right? So I think for the audience in general, I like to present two types of meanings in this case for quantum. One of them is the ability to measure individual quantized particles. For example, the quanta for light is a photon, the quanta for electricity is an electron, and so on, right? So imagine you have a camera, right, a detector, you want to measure one photon. When we try to get to that number, just a few photons or a few electrons, we run into noise issues. You might have noticed that your camera doesn't work as well at night, right? You have more granularity. When you go down to that level, we are at a quantum sensing limit. And so we tend to call this, the jargon is a quantum noise level, okay? You're not sure whether you detected a photon or you detected noise that comes out of the detector. So that's one limit that we can reach with quantum sensors, meaning we can deterministically say, no, that was actually a photon, or that was an electron, or was a particle, without thinking whether it's noise or not. So we can sort of denoise our detection. That addresses directly Suzanne's desire to have extreme sensitivity. You basically get to the physical limit of the laws of physics, okay? The second quantum is one thing that then maybe potentially I'll answer Pri's question with, is leveraging really exotic, somewhat, I would call them magical, but nonetheless existing properties of quantum phenomena like entanglement. The fact that somehow we know that if I measure something in space-time somewhere, that might be seen or recorded elsewhere. What that gives you is this amazing ability to not only have a distributed set of sensors, for example. Think of most of you, because you live in LA, I assume, know purple air, right? So you go into purple air, you look at the map, you know where you want to go or don't want to go, or you want to stay home. Imagine now that all of these sensors actually talk to each other. They're not individual, independent measurements, but they know of each other's existence. You can begin to do extremely sophisticated things, like correlating things that you would never imagine have anything to do with each other, like the butterfly effect. Like something that happened on this particular neighborhood affected down the line something else that happened elsewhere. That, of course, necessitates much more than just sensors, but this is the kind of capability that type of, like the second definition of quantum can give us, right? The ability to correlate events and even predict them. So I wanted to sort of emphasize this because I think it's really important. So now my job is to think, okay, how do we make these two quantum things actually cheaper and deployable? They're entangled, they're on chip, right? So the first step is, let's not go to the on chip quite yet. Let's leverage very well existing technology, particularly in the telecom. So let's use fiber lasers. They exist everywhere, they're cheap, they're very well established, it's an extremely mature technology. And let's prove that some of these ideas actually work well in a laboratory setting. These sensors, what we can do with them is basically provide a fingerprint that is associated directly to whatever the species of the bioaerosol, the diatomic, triatomic, the atmospheric molecule, everything that makes it into the path of this sensor gets its own fingerprint. We can get a library of fingerprints, as many as we can, from all the existing pathogens, all the mold species, whatever we can get at. Once we build that library, in parallel, we can begin to see how do we take these measurements that we can take in a lab from fiber to on-chip photonics. Good news is that On-chip photonics is also a very mature technology these days. It's being used in many of the devices that you carry around, and so it has to do with less with the development of the technology itself, but the methodologies, transferring them from a fiber-based to on-chip. And so that's the ongoing project that my group is leading at the moment.
Thank you. And Sergio, you've already mentioned photonics and the role of photonics in quantum. Could you elaborate a bit on that and where the synergies exist for example, conventional and integrated photonics and the types of quantum sensors we want to deploy?
Yeah, photons are, probably everybody's in this room heard at some point this particle wave duality of photons. They can be particles if you want to, they can be waves. So you really can use them both as classical systems. When we say classical, it means ways that you rudimentarily would have learned in high school or introductory physics, things that actually follow your intuition quite well. And then quantum is more of that esoteric, somewhat exotic, sometimes intuitive, sometimes not at all system. And so photons are quite ideal. They travel, I mean, I work with photons, so of course I will say this, they travel far distances, they don't lose their coherence. What we mean by that is that whatever quantum states we use to define them, they like to keep them for a very long time. They work at room temperature as opposed to other sort of, quantum computing platforms out there. And we actually live by them and through them, and they have an incredible active role in biology. So we can both use them as probes, as something that interacts really weakly with the system and measures it. We can also use them to activate it, to control a system, right? So something that we've been thinking about is down the line after the sensors, how can we not only sense what we have, but can we do something about it? Can we use light to, for example, dissociate, isomerize specific compounds into added value products or compounds that are not toxic, right? So hopefully this answers the question. I could go on and on for this, but yeah, we leverage light both as classical light, think of, for example, as a laser, and we also leverage light as individual photons that can interact and control quantum phenomena.
Thank you. We'll come back to this question of how we might be able to use quantum sensors also in biological settings. But first, I think you've alluded to this already. There's lots of data, lots of measurements, lots of data, maybe data that is taken at various different spots. What can we do with this data, Andrea?
Oh, that's a great question. So I'd like to tell a little story, if I may.
Go ahead.
So I want to say like 14 years ago, I was giving a lecture at one of the national labs in the U.S. I'm not going to say exactly which one, but I gave a lecture about some work I was doing. And one of the lab scientists comes up to me and says, I liked your talk. I want to show you something that I'm working on with, high-dimensional imagery data. Right? So he showed me the idea that he was working on. And it turns out that it happened to be that I had been going around for about 2 years with an idea in my head about how to take large high-dimensional data sets and basically shrink-wrap them to be able to sort through the information. I had this geometric idea in my head. And I was missing one piece of the puzzle, which was how to do efficiently the numerical linear algebra. And this gentleman who introduced himself to me was basically doing exactly that. So I literally sat him down and I said, if you'll permit me, I think we're going to write a paper together. Just sit and listen to me for 20 minutes. And I sketched out an algorithm on his board. I said, I've been thinking about this and I'm missing this, and you're doing that. So here's the pseudocode. Well, fast forward, okay, so we did that. That paper won a prize. And a couple of years later, a colleague of mine who has what are called hyperspectral cameras, right?
Yeah.
So they look at things from a distance, right? They're measuring the electromagnetic spectrum at a distance, and they're looking at fingerprinting of materials, surfaces. And in one specific example, gas plume detection from a kilometer away using standoff detection. And so he sent me an email saying, I'm trying to organize a special session at an international conference on image processing and hyperspectral imagery. Do you want to try to submit a paper? And I thought, well, what the heck am I going to do? And I thought, we're going to try plume detection. So I had my student whose thesis was on part of this work. I said, here's the plume data. I have no idea what it's going to do. She comes back to me like 3 days later with unbelievable results. So here, let me explain the problem. Once you have these fingerprinting methods, suddenly your data may contain many, many sources of different information in it. How do you sort through all of this? Especially when the information that you're getting per molecule or per thing that you're trying to sense has a minimum of 30 to 50 channels, the dimension. In our case, for the plume detection, it was 128 dimensions. And we were looking at video footage where just a few frames was hundreds of thousands of pieces of information, right? My student's running this code in a couple of minutes on a laptop, and it just does everything, right? And I thought, I think this paper's gonna get in, and it did, right? And so I've had a lot of fun working with remote sensing data, most recently working with people at Los Alamos on environmental sensing for surface water detection all over the globe, for multispectral and long-wave infrared data. And so when Pri came to me a few years ago and said, we need a mathematician to work on quantum sensing, and I learned about what it was, I said, oh, do we have algorithms? Oh, yes. So fast forward. So today, I'm working with an incredibly talented group of students, some of whom are here in the room. Can I get you to stand up? Max, right? Stand up, please. Maddie, right? I saw Jack. Jack is here. Wonderful. And there may be more of you, but these three students together over the summer have developed kind of our first prototype of quantum sensing algorithms for high-dimensional data. And we're just at the beginning, but we're so excited about working on this project. Yep.
Thank you. And thank you, students, for standing up. I know we didn't give you a heads up about that. So we have the ability, hopefully soon, to analyze all of this data. How would it impact some of the decision making, and what would we do with all of this analysis, Suzanne? So once we've measured, we've looked at all of this, we have the data, what do we do with it?
Obviously, it depends on which problem we're addressing, but there's just no limit to how excited people will be with whatever additional information we can get. Just to kind of try to illustrate that example, Sergio mentioned the purple air sensors. These are sensors that measure PM 2.5, which is probably the leading cause of death, at least in the developed world, and responsible for something around 7 million deaths a year worldwide. People care about that metric. A measurement for that came out the sensor was developed in like 2013, cost about $10, got put into the purple air sensors. They were taken up immediately within just a few years. Individuals had bought them and put them on their own internet, and the data is being uploaded in real time. It's such a leap forward in sensing. It means that before that we had about 40 government sensors in LA, one of the densest sensor networks in the world actually, but it was uploading data every hour, didn't really do much. With the new purple air sensors, I can figure out if I'm gonna ride my bike, what route I'm gonna ride my bike to work on and avoid the wildfire smoke plume that's coming from Brentwood, for example. It's really amazing. They've currently, to date, they've sold 300,000 of those sensors, and that's the purple air sensors. The total market just for that one metric is about $500 million, which is not a lot compared to some, chips, but it's still quite a lot for environmental sensing. So whatever it is, we will just take it up and use it. One of the things that really stood out to me when Andrea was talking is that one of the problems that we have in environmental science is that in these little sugar cubes of air floating around, there are 500 particles. There's about 1,000 different molecules. They're all at very low concentrations. And the particles are all different. Some of them are bioaerosols, some of them are from diesel exhaust. So having this ability to sort that out and the potential for additional information is just so valuable.
Thank you. Go ahead, Andrea.
Yeah, I just wanted to back that up and say that trying to sort through the signature of many different molecules is tricky. So basically what you have is a single molecule will have a fingerprint that looks like some kind of shape in the electromagnetic spectrum, right? And then let's say you have, I don't know, 10 of these. Well, that's still, assuming that they're distinguishable enough, that's still a reasonably doable problem. But now imagine that your data is actually a linear combination or even a nonlinear combination of all of these things. And so you just have this thing, right? How do we figure out what it is? How do we pull apart all of this information that's encoded? But you might think, well, just one data point, how are you going to do that? Well, actually, you have the ability to collect multiple data points, many, many data points that all have different relative concentrations of these different substances. So that's a problem that is fairly well studied in the remote sensing literature. It's called spectral unmixing. And it's one of the most challenging problems algorithmically to solve. It's something that I have been actively working on recently for remote sensing data, and I'm really looking forward to this challenge with the quantum sensing data. I think it's a very exciting problem.
And just to add to that, we're hoping that we can deploy some of these sensors not just terrestrially, but also on these remote sensing platforms. And the hope is that with a combination of the classical sensors and the quantum sensors that are on board, we have information that we wouldn't have had previously, again, to make some of the decisions that impact human health. I'm going to pass the baton to Sergio. Maybe you could tell us a little bit about some of these devices and how they could also be used in the context of biomedical sensing and more directly impact human health.
Yeah, thanks for the question, because I think this is, the technology spans beyond atmospheric sensing. I'll throw a little bit of jargon out there. What we can do is we can produce what we call frequency combs, light that essentially, if you look at the spectrum, looks like a comb. And if you build that comb properly, it's almost like a perfect ruler, a ruler that has distancing energetically that corresponds to atomic distances. So essentially, that's the main trick that we're playing here. You can apply this ruler to any system, interact with it either linearly or non-linearly, look at how the ruler changes, its comb particular changes, measuring that and correlating that to any particular molecule. And so that is something that can transcend, because this light interacts really weakly with the system. It just passes by. You can really apply this to any sort of system that might interact with light. And guess what? Light interacts with everything. It might reflect, it might absorb, it might get dispersed. And this is the main technology that we want to use, the primary technology that we want to use to do all the sensing, quantum sensing that we've been speaking about. This is a cool thing. Now you can take two rulers, and I won't use my other hand because I'm holding the microphone, but imagine two rulers. There you go. And you can, thank you, Andrea. And you can now pass a molecule, you are sort of sweeping one ruler with respect to the other, and you can enhance significantly that detection, that electromagnetic sort of fingerprint that Andrea was talking about. So we're hoping that this sort of particular technique that we call dual comb spectroscopy or heterodyning can enable this really fast sort of, the fingerprint is basically, imagine how quickly you can take the fingerprint. I'll throw some numbers out there, but in principle, it would be relatively straightforward to take a fingerprint in less than a nanosecond. Nanosecond is 10 to the minus 9 seconds. Nanosecond is the speed at which the chips on your phone work, right? 5G, 6G, we're talking about this kind of speed, if you were to pay attention to that. So that means that, yes, there is a huge amount of variables. There's many different kind of species and concentrations, but we can realistically take this data at really fast rates and then ideally, I pass that problem to Andrea and she figures out this wonderful problem with algorithms and see what we do with all this data, right? But the reality of the sensing being applied to all kinds of biomedical, atmospheric science, or even material science problem is readily available. It's the same trick. It's scalable. It can be, again, distributed, entangled in a network. And it can feed data really rapidly, to answer any question live or quasi-live. So I think this is really the exciting convolution of all these different, the problem set at atmospheric sciences, the technology and the quantum interaction of the technology classically with algorithms is what can help us use this particular case study as a springboard to many other quantum sensing applications.
Thank you. So we could go on for basically forever. But I wanted to open it up to questions from those of you who are here. And and anything is fair game for any of us. And I'll try and moderate as best as I can. Yes, Robert.
You talked about entangling sensors. Now, for instance, for your purple air, you use basically classical electronics to correlate all the data. Can you give me an example where actually entangling would really help to get more information?
Yeah, I tried to explain that earlier, so I'm going to try again, and then let me see if I am actually answering the question. Imagine that I have two sensors, right? And in principle, they're independent. They're just in two different locations, and they've measured both of them something at the same time, and I'm looking at it in my purple air map, right? What I was trying to get at is that because I'm using these combs, these photons, and if I am able, this is a big if, this is another exciting problem. If I'm able to entangle these two different combs, one goes to one sensor, the other one wants to the other one. What may happen is that I might see a signature in this sensor that has to do with the measurement that was taken here, and vice versa. So it adds another very complicated dimensionality to the problem that Andrea was talking about, because I'm not now dealing simply with the measurement with all the variables that this particular sensor has, but some of the features that I see here might be affected by measurements elsewhere. And imagine I have 1,000, 2,000 sensors across LA, right? So you can see how the scales really, depending on who you are, uglily and really interestingly, right? But it becomes this really difficult problem. But the idea is basically that the measurement gets affected not only in this particular sensor when it's entangled, not only by what's present there, but what's present in other locations where the photons are entangled.
Right. And with entangling some of these sensors, in principle, I'm a theorist, so I like to think about bounds, and you can start to saturate the Kramer-Rao bound, for example. And that's something you could never do with any classical network sensor either. So even with classical sensors, we get a benefit from connecting them with each other. But the advantage here is that you could eventually get to something that resembles, say, the Heisenberg limit, which would be really awesome. That is something that is set by the uncertainty bound. It is as precise as you could possibly get. And maybe some of that is not necessary for the problems that are being looked at, but maybe we'll learn something from those data sets that we didn't even expect to see. So.
Can I just add a little bit to that? Lest you think that this is this like impossibly complicated problem, we are fully prepared to simplify it. I mean, we do have actually a lot of techniques where we can design an inlet to just select certain particles or remove the gases and so on. So we can make it a very tractable problem. I mean, these guys can do amazing things, but we can also simplify it at the front end a little bit. Yeah.
Right, I complicate the problem, Suzanne simplifies it, and we iterate. Other questions? Yes, I see a hand there, and I see your hand. Go ahead.
It's become increasingly recognized that migratory birds utilize electron pair qubits in order to sense the magnetic field on a much less expensive and smaller form factor than we're currently capable of. I was just wondering what's holding us back from hitting that form factor, and is there any things we can learn from those systems or to improve ours?
I'm going to pass that question to Sergio, who I know has thought about these.
It's a great question. At the heart of it, not to simplify the problem, but also not to give you an hour-long answer, It has to do with stability. This is just one of the technologies, right? The frequency comb. But if you let it run with the current technology, particularly on a chip, call it temperature, call it humidity, whatever environmental changes there are, the cone is going to start drifting. It's going to move a little bit. We call it jitter. That can introduce a level of noise that we can't really discern necessarily. That's yet another layer of complication for the algorithms that I don't think we can afford. So the research really right now is, and this is why I'm in this chair, this dual comb spectroscopy, this frequency combs has been around before I was born, but my group has become one of the leaders in being able to stabilize these combs for weeks. And so this is a technology that we have in fiber-based that now we are moving into studying how to do on chip. And by that I mean it's not speculative, we know how we're doing it, we're just testing it out as we speak. Yeah.
Go ahead.
You had teased us earlier with a bad qubit makes for a good quantum sensor. Could you go into more specifics on that?
Absolutely. Okay, so something that makes a qubit a bad qubit is that it's very susceptible to coupling to the environment, that you have noise, some decoherence, and several of these things are related to, say, fluctuations in the environment, temperature interacting with something that was not intended for the compute part of the problem. So usually you want to get rid of that, and our colleagues in quantum computing have spent years looking for the next 9 in these qubits. Now, you could take a qubit that maybe has only 1 9 or something that isn't particularly good for a compute application, but it would make a very, very precise sensor. So be a very good sensor. And for us, the challenge is not the sensitivity of individual sensors, but also how we connect them to get closer to this Kramer route bound. So the issue with some of the sensors, particularly ones that operate at low temperatures, are the form factor, and that's something that was alluded to already. But the photonic quantum sensing platform is something that you could think about doing at room temperature. The other piece of that is that doing photonic quantum computing at room temperature maybe is a little ways out, but doing sensing at room temperature is something that's here, and that's going to leverage some of the telecom technology that exists. And I know there are folks here in the audience who've worked in that field that uses components that we know how to build cheaply. So this is, again, something that has more near-term impact. Yeah. Yes?
Sort of follow-up to what you just said. I've never heard of the purple air product. I just looked that up, and so that's like a part of the counter. Sergio, obviously, you're a laser guy, you do lots of lasers. I'm wondering, what are some practical non-optical quantum sensors that are used today for atmospheric sensing? Or is everything pretty, or are there some reason that optical is?
To the extent I know, and Suzanne will know this better, all the atmospheric sensing technologies that we have are classical. We don't have any quantum technology. And the reason why we choose photons, among other things, is because of what Pri alluded to. Any other quantum platform of any sensing these days, however sophisticated, it requires either cryogenic, yeah. So if you really think about, this is really, I think it's a really, she said it already, I'll repeat it because it's a really important point to make. If we want to make quantum sensing for biochemistry, for atmospherics, whatever reality, whatever case of reality now, we have to use photons. Right. It's the only practical, cheap, and a scalable way to do it. Yep.
Yeah, folks have been thinking about defects in wide bandgap semiconductors, including diamond or silicon carbide, and those can be really good sensors in principle. Those have been thought about more for, say, biomedical applications, because again, they can be, brought to close skin contact or eventually even embedded, but not necessarily for the types of environmental applications yet. And there's some scaling challenges, stabilization challenges, but all things that are being worked on and will be worked on, because some of these problems will be solved on the compute side or even on the networking side.
And just to briefly add to that, it is an engineering problem. We know how to do this. It's not we're not hitting a basic limit in physics, yeah.
Right. Manny, go ahead. Yes, please.
Excuse me. Recently,
a sign if there's some light there. And what kind of sensor do they use? Do you think quantum sensor could be useful for other life-sustaining chemicals?
Do you want to
I
take
can-
a stab?
I can
Okay,
take a
go
stab
ahead.
at
and
that,
then
yeah.
I have lots to say about this. Go ahead, Sergio.
Well,
You get
then-
like 30 seconds.
Okay.
Go.
Yeah, the sensors are based on sort of radiation detectors, where you can quite well discern the atmospheric content of any particular exoplanet or stellar body by looking at the spectrum that it emits. Basically, and the signatures, the specific signatures, you look at the spectrum through telescope and imaging, astronomic imaging, can be quite accurate, even providing a level of temperature and so on. These are still classical sensors. And to be honest, it's a really interesting question to think about how we can take that to some of the ideas that we're developing here. I'll
It
pass
would
it.
absolutely help. In fact, launching some of these sensors on future space missions is something that we're collaborating with colleagues at NASA JPL on. But even before that, we've been thinking about how these could be launched onto, say, satellites that exist in orbit, and how connecting some of these, so essentially this idea of a network of clocks has been around for a bit, but that could be used for other kinds of fundamental physics searches as well, including searching for things like axions, my personal obsession, and other ways of actually tightening the bounds on this type of radiation that we're detecting and the sources of it. Right? So eventually, if you think of it, we're backing out information from data that is very indirectly measured. So it'd be helpful if, for example, we didn't throw away any photons, types of sensors that Sergio is building, but also could collect it in a way that we have more spatial information, and in that case, it'd be very large spatial information. Yeah. So, but I'm excited to tell you more about this. Yes, Raza, go ahead.
Yeah, I want to say congratulations. I mean, that's a fantastic idea. In creating quantum network connecting distributed quantum sensing, I think is great. It's really needed. But the question I have, when you have your quantum network and your quantum sensor connecting together, what I understand, you're going to process data digitally or classically. Do you see a version of your distributed sensing that the quantum information is also processed quantumly or analog using neuromorphic or quantum computers?
I think I can help.
Wait. Okay, let me qualify that with I am not an expert on quantum computing. That would be Pri. So it's a really good question. I think for starters, we're going to be post-processing data in a more classical way. But some of the algorithms that we are developing and will continue to develop will need to respect the quantization of the data coming in, right? So current methods from remote sensing, it's all continuum, right? Right, and so we need to be looking at modifying the method, and from the classical image processing community, for example, like we do work with data that has low photon count, like that's something we know how to do, and there's statistics that you use for that, but this has to go beyond that, right? Right, so I think it's at first, the post-processing, but then, of course, you want to ask, what can you do in real time, and what is real time, right? Is real time this infinitely small time scale of the device, or is real time the time in which you need to know the information? These are all really good questions.
There is a small but growing effort on the quantum computing side, and how there are algorithms that could work with quantum data sets. It's just a very, very new field. There are a handful of groups who are working on it. We've introduced a couple of things in that domain, but never with actual data sets that have been measured and done something with it. Both because the quantum devices where we're thinking about implementing these algorithms are smaller than we'd like them to be, and also because some of these data sets have just come to be. So.
Yeah, it's also, I wanted to also mention that if you're measuring atmospheric, information, pollutants and things like that, like you do when you look for the bike paths, right? One of the things that we'd like to be able to do is not only measure but predict, right? And so to predict, we already know how to do that to some degree, right, with weather and things like that, right? But we'd like to be able to to figure out how to do in a very sort of precise and modern way with machine learning to be able to say, well, okay, this is how it is now. How do we do the data assimilation so that in the future, 5 hours from now, what will it look like? How can I plan my day, for example?
All right, we have time for one last question. So go ahead.
Thank you for an excellent discussion. I think this is fascinating. I'm a non-physicist scientist. I'm a physician. I'm a pulmonologist. And I think it's just important to put this whole discussion into context of the profound effect on these particles, these PM 2.5 on human health. Large particles are rained out in the upper airway, expelled by mucus. These small particles get down into the alveolar sacs, or can be absorbed into the bloodstream, and they are the mechanism by which the polluted environment that we live in can affect human health. They absorb these benzene, carcinogens, all these various compounds can be absorbed onto these PM 2.5 particles and get entrance into the body in that way and cause cardiovascular effects, malignant effects, et cetera, et cetera. So I think that I just wanted to put it in context that it's very important, the work that you're doing, be able to sense it, hopefully identify them, and then hopefully be able to mitigate them.
Awesome. Thank you.
Wonderful. Thank you, Jim. Well, time flies, right? It's amazing. It's been a little over an hour already, so I think it's probably better that we call it a fantastic panel. So why don't you join me and thank our panelists for a really interesting discussion. Well, we certainly hope that you found today's event not only insightful and thought-provoking, but also impactful. I think the possibilities are many, and I really like the message that quantum sensing is really here today, that there are opportunities to be taken. We're looking at one particular platform, but there will be others that will be developed here at UCLA and elsewhere. So keeping an eye on that, I think, is going to be very, very exciting. Well, I want to thank some of the people that, of course, events like this don't happen sort of on their own. So I want to thank our events manager, Andrea Corrales, for all her work making this possible. I don't know if Andrea is yet. Is she here? So if you would like to learn on how you can support our faculty research featured tonight, please contact me or our development team. Brooke Sanders, I think Brooke's here. Are you here, Brooke? Brooke's in the back. And also Lloyd de Leon, right here, sitting in front with me. So please feel free to contact us. And thank you very much for being part of today's event. We hope that you have a great rest of your night. And we eagerly anticipate our next event for you to join us, where we can continue our discussions and foster new collaborations. So thank you very, very much.